Okay, so today we are talking about Heapsort. Now in the last video I showed you guys how we can construct heaps and the general theory behind the data structure, but now we are moving up a level. I'm going to start explaining how we can use that data structure in useful ways, and a very good example of this is Heapsort. Heapsort is quite a fast sorting algorithm which uses the properties of max heaps in order to sort arbitrary arrays of data. Now, the first thing we're going to have is an array of data, right? So here I've got an array containing 8 elements. These are all integers. Now if I was to construct a binary tree out of this data, it would look like something like this. So I have 1, 15 and 5. 1's the parent or root node of the whole tree. 15 and 5 are the left and right child nodes respectively. Then of course, as we build on the tree, 12 and 3 are the child nodes of 15. 4 and 7 are the child nodes of 5, and then 8 is the child node of 12, the left child node. Now I'm going to add some indexes here in the array to make it easier to visualize, and then I'll add the corresponding indexes to nodes in the binary tree. Now Heapsort has 4 different steps. The first step is that we have to build a max heap out of this binary tree. If you guys aren't sure what a max heap is or how we construct one using the bottom up approach, I made a video last week explaining how this process works, so I'll leave a link to that in the description. You guys can check that out after watching this video. The second step is going to be, we're going to swap the first and last elements, and we're actually going to shorten the array each time we do a swap. If you guys don't understand what I'm trying to say, that don't worry. When I start running through the algorithm, it'll make a lot more sense. But understand that these swaps will get shorter and shorter over time. The third step is we're going to heapify the first element. And then once we heapified it, we're going to do the fourth step, which is repeat steps 2 and 3 until we reach the last element in the heap, so we can't swap anymore. I'll go through this step by step so you guys can understand what I mean by all these different procedures. So let's start off with the first step, which is turn this binary tree into a max heap. We're going to do that quickly right here. The algorithm which you could use is a bottom-up approach. Once again, I explained in the last video. So now that we've got a max heap, let's do the second step, which is swapping the first and last elements. In this case, the first element is 15 and the last element is 1. So if I was to swap these two, I'll get a new max heap, right? Oh, this is not actually a max heap just yet because we have to heapify it to make sure it satisfies those properties. But one thing I want you guys to notice is that I'm going to mark the index or the line just before 15 red. What this means is that 15 is no longer going to be considered to be part of this heap, right? So what I'm going to do is just grey out the node 15 because in future operations we will not consider it to be part of the heap. It will be something separate at the end. Now if I do the heap, if I heapify it now, I'll first swap 1 and 12 because 12 is the largest element in this little subtree, and then we have to do it recursively. So here I have 1, 8 and 3. 8's the greatest out of these 3, so I'll swap these 2 again. And that's one iteration of this algorithm complete. Now we can go through the next iteration. So now we're going to swap the elements 1 and 7 because remember, the index 8 is no longer part of the heap, so 15, I'm just going to ignore it from now on. So if I swap 12 and 5, I'll get this binary tree. So now if I heapify it, actually before I heapify it, I'm going to grey out the 12th node, or the node at index 7, because now that's no longer going to be part of the array, okay? I mean part of the heap. So if I do the heapify operation again, I swap 5 and 8 because it's the biggest. And now if I look at the second subtree where you have 5, 1 and 3, 5 is the greatest at all of it, so we can just stop there. We can move on to the next iteration. Something you might notice now is that index 8 is 15 and index 7 is 5. Index 7 is 12. So we're going in a decreasing order. Now what we do is we repeat these steps until we get one element left, so we can't make any more swaps. And by the time we get there, the whole array will be sorted in ascending order. So I'll walk you guys through each step of this, right? So if we do the next swap, we swap 1 and 6, so we have 4 and 8. We'll grey out 8 because now it's no longer part of the heap. And then if I do a heapify on the first element, we swap 4 and 7, right? Because 7 is the biggest number there. Then we can do another swap. So we swap 1 and 5 because we're on step 2 again. And then we can do another heap sort, or rather before we do the heapify, I'll blur out 7 because no longer part of the array. And we can now heapify from element 1. So out of 3, 5 and 4, 5 is the greatest element, so we're going to swap 3 and 5. If you try looking at the next subtree, so we have 3 and 1, 3 is the greatest out of them, so we're just going to leave it there. The next thing is swap 1 and 4, right? So we have 1 at the top, and then I will remove 5 from the array. So then if you heapify that, because 4 is the greatest, we get this. And then we just step through the rest of the algorithm. So we swap again, remove 4, swap 1 and 3, swap back. And then by the end of it, we get one more element, which is 1. And we can't swap 1 with anything else because it's the last element, nothing to swap with. So then I just mark this as done. So at this point, if you look at the array, it's sorted in ascending order. So we've got 1, 3, 4, 5, 7, 8, 12, and 15. And this is how Heapsort works. We just repeatedly follow the steps of swapping the first and last element, and we heapify it, and then we decrease the index of the element we swap by 1 each time until we get to the last or the first element in the array. Now if you're wondering what the time complexity of this algorithm is, it's of n log n. So it's a little bit more than logarithmic time, which is quite fast. It's quite decent. It's not as fast as some other algorithms like quicksort on average, but it's faster than bubble sort and insertion sort, I think. So it's quite a good sorting algorithm. So now I will show you guys how we can write down. So I wanted to show you guys this school community I made. So right now we have a pre-sale, but this community is all around learning C and how we can program efficiently in C and make performance software. So of course we're going to have one-on-one Q&As with me every week. You can DM me if you got any questions. I'm going to create courses on portfolio projects, so you know, something like a game engine or maybe a game or something that you can actually put on your resume and show off to your employer if you want to, you know, progress your career. I will also have a library of tutorials on C. We have guides on memory management, data structures, algorithms, and a lot more. So right now we have a price of $30 or £30, and after the pre-sale it's going to double to £60, right? So this is probably the best time to actually get the membership, because if you get it at £30 right now, it will stay that way for the rest of the time you're in the community. Now if you watched this far in the video, I'm assuming that you are interested in education, right? Because most people, they won't watch this video this far, they won't be this interested. So if you have watched it this far, you're probably interested in this, so please check it out. Okay, so I've got the code from the last tutorial, and I've added another array right here called the second unordered array, which is 1, 15, 5, 12, 3, 4, 7, 8. I've got 2 different arrays here just to show you guys that, just to make sure that the algorithm actually works upon multiple arrays, so we don't have like any edge cases. So the Heapsort algorithm is pretty simple, but before I write the algorithm, I want to write a quick function here called print array. Now print array will just take in an integer array, of course array, then take in a count, right? And I'll just print it out for us in a nice way. So I'll just say printf array, right, count at 0, or array at 0. Then for int I is equal to 1, I is less than count, I plus plus. I'm going to make sure that the user actually provides a valid index, right? I mean a valid count, so if the count is less than 0, then obviously there's no elements in the array. Usually that's a mistake because they might have the variable they passed in might be incorrect, so we're just going to return early if that's the case. Otherwise we'll just print out the array element by element. So if I do something like print array unordered array, then array count unordered array. So you get 1, 15, 5, 12, 3, 4, 7, 8, right? That's what we're expecting. So it's printing out the array for us. Now let's do heap sort. Let's write the function heap sort. So we're going to pass in the array. I'm going to pass in the count. I'm actually going to call this heap. So the first step is we have to turn this binary tree right now into a max heap. So how can we do that? We can just run the heapify bottom up method or function we just wrote here, right? So I'll pass in our heap, pass in the count, then I'll pass in true. So I've got this comment right here which says that if max or min is true, then we are going to turn it into a max heap. If it's false, we're going to turn it into a min heap. So in this case, we're going to turn it into a max heap. So we're just going to do that. Then I'll quickly just print out the array to show you guys that it actually worked. Right, so forgot to run it. So here we go, we've got a max heap, and now we can start running the rest of the algorithm for Heapsort. So I'm going to create a variable here called valid index. I'm going to set that equal to count. And then I'll make sure that valid index is greater than 1. And as long as it's greater than 1, I'll decrement it by 1. So what's happening here is we have the actual count, which is the whole array, right? The actual size of the array. But each iteration or each pass, if we were to say, in each pass of the Heapsort algorithm, we're going to decrement this index by 1. But I don't want to decrement the count because the count keeps track of the whole thing. So I'm going to create another variable called valid index, and just tells us the slice of the array that we are working with. So we know the ends of it, so we can swap the values as you want. And I'm stopping before 1 because once you get to 1 element, that means the Heapsort algorithm is terminated, right? It's finished. We finished sorting. So I'm going to create a variable called temp, which is going to be the first variable inside of the array. Then I'll swap the first element with the last element, or the last valid index, right? I do -1 because we're indexing from 1 here, but we actually have to -1 to get, because the arrays are indexed from 0. And then I'll set the valid index next to 1 equal to temp. So I'm just doing is I'm swapping the first and last values in that side of the slice that we have of the array, and that's just going to be, I have to store the temp value here because when I store this value, when I store the last element here, I lose the original value of heap 0. So just store that there so I can set it right there. Okay, and then once I've done that, we just have to run heapify on it, on the first element. So just, if you look at the arguments, you pass in the heap, we pass in the index, which is 1, and then I pass in the count. So the count is going to be valid index -1. And then I pass in true because it's going to be max heap. The reason I'm minusing 1 from it is because if you look here, on the first iteration of this loop, I'll just quickly fetch this array right here. On the first iteration of this loop, actually, if I just get this, because that's the right one. So I will first swap 15 and 1, right? So this will be 15, and this will be 1. And then if I try heapifying from 1, it's going to bring 15 back to the start, and this will be and then if I do the next loop, it's going to do 5. And then it will just end up like swapping the values back to where they were before. So I want to swap the values at a valid index, and then I want to run Heapsort on the values just before the index is swapped. So I swap 1 and 15, but I run heapify on 1 through this, right? Just before this last element. Because once we swapped it, we no longer care about what it is because it's in the right position in the array. So just do valid index -1, and then in the next iteration we minus it, so we know that the actual last element we're going to swap. So that's it for the Heapsort algorithm. If I just run it now, and then I'll just print out a before and after, right? So I'll do print array, unordered array, count unordered. I'll do an after as well. Right, so there we go. We just sorted the heap. So before it was 1, 15, 5, 12, 3, 4, 7, 8. now it's 1, 3, 4, 5, 7, 8, 12, 15. So it's ordered the array in ascending order. If I try another one, so right, we used to try this first one. I'll just remove this, we don't need that. It also ordered this, so 5, 10, 15, 98, 4, 13, 5, 61, 49, 2. That's the wrong order. Then now it's 2, 4, 5, 5, 10, 13, 15, 49, 61, 98, right? So it handles duplicates as well. And that's pretty much it for Heapsort. It's quite a simple algorithm once you understand how it works. And a lot of the functionality we needed, so the heapify and the heapify bottom up. So just turning the binary tree to a max heap, then heapify. We already wrote that in the last tutorial, so we just had to just use those functions again in this way. So I hope you guys liked the video. If you did, please leave a like, comment, share, subscribe. And if you've got any questions, I'll be happy to answer them in the comments below. So please feel free to ask. And I'll leave the code for this tutorial in the comments, in the description as well, and the link to the school community. So thank you guys for watching, and I'll see you guys later. Bye.